All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for HL Chemistry as we're moving through topic 1 with stoichiometric relationships. And now we're about to shift into something that's very conceptual. There's not a lot of calculations for what we're going to look at in this particular video, but it's going to be extremely important and it's foundational to our understanding for how gases behave the way they do, specifically when we start talking about ideal gases, right? And so what you should be able to do by the end of this video is to solve problems and analyze graphs that involve the relationship between temperature, pressure, and volume for a fixed amount of an ideal gas. Okay, so we're essentially going to be looking at some gas laws, looking at the graphs of those laws, and what we can deduce from those pieces of information. Okay, so let's go ahead and dive right in here as we look at gases. And we're going to start with the kinetic theory of matter. And when you think about the kinetic theory of matter, this is when you guys, like when your teachers, when I've asked you, when other science teachers have asked you, can you draw what a solid looks like at the particle level? Can you draw what a liquid looks like at the particle level? Can you draw what a gas is going to look like at the particle level? You're using the kinetic theory of matter when you're using those particular diagrams. And if you recall, the kinetic theory of matter just simply communicates that all matter is constantly moving to some degree. Now, for some particles of matter in some states, that means the movement is a lot more pronounced. Some of it, like with solids, just means that the particles are vibrating back and forth. And so when we look at the kinetic theory of matter, specifically as it pertains to gases, what it communicates is there are 5 assumptions that we're operating under so that we can talk about an ideal gas. The first being that the volume of the gas particles is assumed to be 0, right? Because when you start to think about how big the gas particles are as compared to the volume of the container, we can assume that the volume of the gas is 0. Now, we obviously know that the actual volume of the gas is not 0, so we know that there's some flaws and limitations here. But when we start talking about ideal gases, that's the assumption we operate with. The volume of a gas is assumed to be 0. The second assumption we make with the kinetic theory of matter is that the gas particles that make up our substance that are in their container are in constant motion, right? Because there is a temperature that's being measured, and temperature is a measure of average kinetic energy. And so the particles are going to be moving. Some are going to be moving faster, some are going to be moving slower, some are going to be moving at that average speed, but the particles are going to be in constant motion. The third thing we assume, or that we're going to use to make these conclusions and use the ideal gas equation, is that the collisions of the gas particles with the sides of the container cause pressure to be exerted. Right? So as the particles are moving inside the container, they're hitting each other, but they're also hitting the sides of the container. And as a result, that's creating a pressure within that particular vessel. The fourth thing that we need to talk about as it pertains to kinetic theory is that the particles exert no forces on each other. And specifically, we're referring to those intermolecular forces. Right? So when you have individual gas particles, whether they're atoms or molecules, we're going to assume that there are no intermolecular forces of attraction between similar particles. Now again, we know, hopefully you remember from AP that it's a false assumption because there are going to be forces that exist, but in terms of an ideal gas, we're going to assume that those forces exerted are negligible, that there are no forces being exerted on that substance. And the fifth thing that we need to talk about is that the average kinetic energy is going to be directly proportional to the Kelvin temperature of the gas, right? So remember, temperature is a measure of average kinetic energy. And the nice thing about Kelvin is that it doesn't have any negative values because kinetic energy can't be 0 or can't be negative. It could be 0 if it's not moving. But average kinetic energy is not going to be 0 for a gas because it's going to have a Kelvin temperature where it's going to be moving, right? And so the higher the Kelvin temperature, the higher the average kinetic energy of our given substance. right? And so these are the 5 assumptions that we use when we start talking about kinetic theory, kinetic molecular theory, and how that pertains specifically to gases as a whole. Hopefully that makes sense. Hopefully you're remembering some of this as we were talking about it last year or whenever you had chemistry last, right? So that's kind of the operating assumptions we use when we're talking about how gases behave. So volume of gas is 0, the gas particles are in constant motion, the collisions that the gases have create pressure, the particles don't exert forces on each other, and the higher the Kelvin temperature, the higher the average kinetic energy of our particles. Now, some properties of gases that we're probably pretty familiar with, that there's no definite shape, they have no definite volume, they're very easily compressed, they have a high rate of diffusion, they can move within a large space very quickly based on the masses of them. Obviously, higher mass particles move slower than your lower mass particles. And then what we know is gas particles exert pressure on their surroundings. Now, this is not an exhaustive list of properties of gases, but these are things for us to kind of keep in the back of our mind that help us kind of readily go back to, okay, this is what we're talking about when we're talking about gases. Now, when we're dealing with gases, you may recall that it's extremely important that you always use Kelvin temperatures when you're working with any sort of gas law problem. And that just has to do with the fact that we're talking about kinetic energy having to be at least 0, it can't be negative, and so that's why it's so important to always use those Kelvin temperatures. So anytime you're given a gas law problem, go ahead and convert those temperatures over to Kelvin. And remember the conversion there, Kelvin equals the Celsius temperature, and just add 273 to it. And remember, 0 Kelvin, negative 273 degrees Celsius, is called absolute zero, and this is the temperature when all motion theoretically ceases to exist within a particle, right? You can also probably heard that as like heat death, because you've removed all of the thermal energy, and so we're causing particle motion to stop. Now, this is theoretical. We haven't actually achieved absolute zero in any lab conditions, but it's a theoretical where all particle motion would stop. Now let's dive into some of the laws. So we've got a couple laws that we need to take a look at before we look at the ideal gas equation. So you got Boyle's law. So Robert Boyle was an Irish chemist, and he discovered that the volume of a gas was inversely proportional to the pressure applied to it. Now you might be thinking, Mr. Kenton, what does that mean? Well, what that means, if you increase the pressure, the volume is going to decrease, right? Or vice versa, if the volume is increased, the pressure is going to be decreased, right? And the equation that best explains Boyle's law is P1V1 equals P2V2, right? So pressure in our initial container, volume of our initial container, as long as the same mass and temperature are constant here, then if the pressure changes, P2, so P final times V final, right? Now, here is a graph of pressure versus volume. So you've got pressure on your x-axis, volume on your y-axis, and you can see that we've got that decay where volume's up, pressure's down. But when pressure's up, volume is down. But then when you take pressure and compare that to 1 over the volume, then you get that linear relationship. So Boyle's law shows us that the pressure of a gas is inversely proportional to the volume of that gas, as long as the temperature and the mass of gas are held constant. Those are 2 important pieces that we need to make sure we always go back to there. Now, Charles's law, from Jacques Charles, who's a French physicist, and he discovered the relationship between temperature and volume at constant pressure. Again, it's also assuming that you have constant amount of gas as well. He was the first person to make a solo balloon flight and it was on his flight that he discovered that the volume of a gas was dependent upon the temperature. And so what he discovered was that the volume of a gas is directly proportional to the Kelvin temperature. So if we simplify that, what does that break down to? If you increase the temperature, the volume of your gas is going to increase as well, right? Think about it when, for example, like with car tires, when it's in the summer and you're riding in your car, what tends to happen is that the volume of the tires, they tend to get a little bit larger because of thermal expansion, right? The tire is heating up, the gas particles move around more, so they expand and they cause the tire to have a bigger volume, but you still have the same amount of particles that are present. Now, the relationship with Charles's law, so temperature 1, volume 2 equals T2, volume 1, right? So that's if you're thinking about it in terms of without any kind of division or anything there, but if you put your temperatures and volumes together, you'd see the relationship pretty easily, right? Now, here's the graph of volume versus temperature. It's linear, and so that's how we're able to say, all right, because we have this linear relationship between volume and temperature, then we know that the volume of a gas is proportional to the Kelvin temperature. So as one goes up, so does the other, right? At any given point, if volume increases, assuming that pressure and amount of substance are being held constant, the temperature should be going up as well. We've got Gay-Lussac's law. So Joseph Gay-Lussac was a French physicist and a chemist. Again, we've got these balloonists. I guess people back in the day, they just enjoyed playing around with balloons. I don't know. But he discovered the relationship between temperature and pressure. And so, again, some things that you have to consider here. We have constant volume and constant amount of substance. If you increase the temperature, then the pressure is going to increase, right? And if you think about this from a very practical example, that's why it's important that you don't heat like aerosol cans that are pressurized. They always have the label on them that warns you, hey, don't expose to high heat, because what's going to happen, the volume of the container is not changing, the amount of substance is not changing, you're increasing the temperature, so you're going to increase that pressure to where the can could burst, right? Now, Gay-Lussac also invented many types of chemical glassware that we still use today, which is pretty cool. And so the relationship that he came up with, this idea of T1 times P2 equals P1 times T2. And so when you look at this from a graphical perspective, again, you're going to have, now I do think this is important. So notice that we've got pressure versus temperature, one where it's in Celsius and one when it's in Kelvin. And this is why it's so important for us to use that Kelvin temperature, because we see these relationships so much more distinctly, right? So notice that, yeah, it does seem like the trend is that as pressure increases, temperature increases, but it doesn't seem that stark or that significant. But when you convert it and use that Kelvin temperature, you see very clearly we've got that linear relationship where pressure goes up, so does temperature, right? And so from these graphs, we're deducing that the pressure of a gas is directly proportional to the Kelvin temperature. Now, what effect does temperature have on gas volume? So if you double the temperature and keep the volume constant, then the pressure is going to double. If you double the volume and keep the temperature constant, the pressure is going to be halved. So the first one there, when we're looking at volume being constant, temperature and pressure, we're looking at Gay-Lussac's law. The second one here, we're looking at Boyle's law. You double the volume, keep the temperature constant, the pressure is halved. And so, therefore, the net overall effect of doubling the temperature and doubling the volume is that there is no overall change in pressure. Now, that's considering if you do both of those things. If you double the temperature and double the volume, then there's going to be no change in the pressure. That should make sense from a mathematical perspective. Think through that. If you need to pause the video and kind of think through that in your brain, take a look at that, but that should make sense to you guys. All right, we got Avogadro's law. Avogadro was a busy man, right? Italian chemist. He postulated that equal volumes of gases at the same temperature and pressure contain the same number of particles. And so for a gas at constant temperature and pressure, so those are our constants, right? What we know is the volume of gas is directly proportional to the number of moles of a gas in its container. So V1 N2 equals N1 V2. And then our last equation we're going to look at is the combined gas law. So you can combine each of those three gas laws that we just looked at. You've got Boyle's law, Charles' law, Gay-Lussac's law, and you can combine those into one equation. Now again, remember you got to use Kelvin temperature. And so in this particular case, if you're having to use combined gas law, you're going to be given 5 knowns and you're asked to solve for 1 unknown. And the relationship without any of like the division in there, it's just one kind of thing. P1 V1 T2 equals P2 V2 T1. Now if you want all of your 1s and 2s on the same side, that's a pretty easy fix. You would divide both sides by the temperatures respectively and get them on the opposite side. So P1 V1 over T1 equals P2 V2 over T2. Okay. And so that's our combined gas equation, and that allows us to relate all of those three gas laws together. Hope this was helpful, Asian. Hopefully this is a good reminder of all the different gas laws in kinetic molecular theory and some of the assumptions that we make as we kind of transition here into the ideal gas equation. Thank you guys so much for watching this. I look forward to seeing you guys again soon. Take care.